Out of 4,000 missiles fired at a single target, not one hit. This isn't legend. This isn't exaggeration from enthusiastic historians. This is a confirmed, documented fact of military statistics that still baffles air defense specialists today. Now, a question you've never been asked. What if this machine's absolute invulnerability wasn't built on flawlessness, but on an officially concealed flaw that, on the ground, looked like a shameful manufacturing defect? What if the metal in its frame wasn't sourced domestically, but was secretly purchased through dozens of shell companies from the very state this machine spent years spying on? We're opening archival documents rarely mentioned in popular retellings. We're going to show you an engineering decision born not out of triumph, but out of a superpower's national humiliation. A decision so audacious that modern engineers still haven't managed to replicate it. Watch until the end. And you'll learn why an aircraft that literally wept fuel onto the airfield tarmac became the most unreachable target in the history of aerial warfare. This isn't a story about a perfect machine. This is a story about how deception, defect, and trauma created something that, to this day, has never been surpassed. 3 in the morning, Beale Air Force Base, California. A technician. The name doesn't matter. There are hundreds of stories like this one, and they all start the same way. Walks along a darkened hangar with a flashlight in hand. The beam sweeps across the concrete and stops. Beneath the fuselage of the most secret aircraft on the planet, a puddle is spreading. Kerosene. Slowly, rhythmically, drop by drop, it seeps from the seams in the skin straight onto the floor of a military airfield. As if the machine built by the finest engineers of a superpower, the machine that cost billions of dollars, the machine whose very existence was known to only a handful of people, had simply sprung a leak. Like an old gas can. Like a rusted bucket. The young technician looks at this and feels exactly what anyone in his position would feel. Shame. Confusion. A thought that forms on its own. We built this for billions, and it leaks like a bucket with a hole in it. He doesn't know what only a few people know today. He doesn't know he's looking at a malfunction. He's looking at one of the boldest engineering calculations of the 20th century. He's looking at a decision made by people who deliberately designed in a flaw, because without that flaw, the aircraft would simply have torn itself apart in the air. This is the story of the SR-71 Blackbird, and it is not a story of triumph. The official version, the one that lives on museum placards and glossy aviation magazine pages, tells you about a flawless machine, the pinnacle of engineering thought, perfection born of American genius, decades ahead of its time. A pretty picture. A convenient picture. It's a lie. The truth is far messier. The truth smells like kerosene on concrete, carries the bitter taste of deception, and rests on the honest word of a metal that was supposed to melt and didn't. The skeleton of this machine was forged from titanium purchased secretly through dozens of shell companies from the very state this machine was built to spy on. The skin of this machine was engineered to leak on the ground and seal itself only in flight, only from the hellish friction against its own air at a speed 3 times the speed of sound. More than 4,000 missiles were fired at this aircraft over the course of its career. Not one hit its target. Not once. This isn't luck. This isn't legend. This is documented, verified statistics. And behind that statistic lies not armor, not trickery, not magic, but a decision that would have struck any engineer of the previous generation as insane. The machine's only defense against death was to simply push the throttle to full. Today, we won't tell you a fairy tale about a perfect aircraft. We're going to open it up. For real. The way a pathologist opens a body, without sentiment, without gloss, without deference to the official legend. We call this method the breathing metal protocol. Why breathing? Because this aircraft literally breathed. Its skin expanded and contracted with temperature like the lungs of a living organism. Its seams opened on the ground and closed in the air. Its structure wasn't a static hunk of metal. It was a system that existed on the edge, balancing between destruction and flight every single second of its existence. The breathing metal protocol isn't a metaphor for the sake of a nice turn of phrase. It's a literal description of the engineering philosophy behind this machine. Every element of the SR-71 structure that looks, at first glance, like a flaw, a shortcoming, a superpower's shameful defect, turns out, on closer inspection, to be a precise calculation, engineered down to the millimeter. The engineers who built this aircraft deliberately designed in weakness. They built fragility into the structure because they knew rigidity at this speed, at this temperature, meant death. Imagine a material that has to be strong enough to withstand the stresses of flight at 3 times the speed of sound, and flexible enough not to crack when its temperature spikes by hundreds of degrees within minutes. Imagine an engineer tasked with building an aircraft out of a metal that almost no one in the world at that time truly knew how to work with. Imagine a team that understands. If they build everything perfectly flush, without a single gap, without a single seam, the aircraft will tear itself to pieces on its very first supersonic flight, the moment the metal begins to expand from the heat. And that's when a solution is born that looks insane on paper and brilliant in the air. Don't fight the metal's expansion. Give it room to expand. Leave gaps. Let the skin literally weep fuel on the ground, at rest, in its cold state, knowing that the moment the machine gathers speed, the moment friction against the air heats the fuselage, those same gaps will close, those same seams will seal, and the aircraft will become airtight at exactly the moment survival demands it. This isn't a malfunction. This is breathing. And this is only the first of 5 phases we'll open up today. We'll begin with a phase we call the cold seam. We'll unpack one of the most cynical and, at the same time, most brilliant deceptions of the Cold War, the story of how titanium, needed to build an aircraft to spy on the Soviet Union, was purchased from the Soviet Union itself, through shell companies, through intermediary chains in third countries, through a system of deception worthy of its own spy thriller. You'll learn why the United States had no titanium of its own of sufficient purity, and why the engineers building America's most secret intelligence weapon were forced into a deal with an adversary who had no idea the deal even existed. Then we'll move to a phase we call the leak point. We'll return to the very image we opened with, the puddles of kerosene on the concrete of a military airfield. We'll break down the physics of thermal expansion in titanium panels at speeds exceeding 3 times the speed of sound, and explain why engineers deliberately left gaps where logic would suggest sealing them shut. You'll learn how the very same flaw that made a technician blush with shame on the ground turned into perfect airtight integrity at 25 kilometers of altitude. After that, we'll enter the phase called the thermal threshold. Here we'll talk about the philosophy behind the entire design, an aircraft engineered not despite extreme heat, but because of it. We'll examine how the skin glowed at hundreds of degrees at cruising speed, how fuel served not only as propellant, but as a coolant for the cabin and electronics, and how crews lived with the constant knowledge that their machine operated at the very edge of failure on every single flight. Next comes the phase called the afterburner escape. This is, perhaps, the most dramatic part of our investigation. We'll break down a tactic that sounds like a joke on paper and turned out to be a completely viable survival strategy. Just hit the gas. You'll learn how the missile launch warning system worked in the pilot's cockpit, what happened in the first seconds after the alarm sounded, and why no missile of that era could physically catch a machine at full afterburner. We'll unpack a statistic that sounds impossible. More than 4,000 missiles fired at this aircraft over its entire career, and not a single hit. An absolute survival record unmatched by any production aircraft to this day. And finally, we'll close the investigation with a phase we call tempering. Here we'll draw a direct line from the SR-71 to its predecessor, the U-2, and to the incident that permanently changed the philosophy of American intelligence. We'll talk about pilot Gary Powers, about his aircraft being shot down, about the captivity that became a national humiliation for the United States. We'll show how every flaw of the SR-71, every detail we unpack today, turns out to be a direct answer to that trauma. The philosophy was simple and ruthless. If you can't be shot down, you can't be captured. 5 phases, 5 parts of one body, each one balancing on the edge between destruction and flight, between what looks like a malfunction and what is, in truth, the calculation of genius. We're not going to tell you about a flawless machine. We're going to tell you about a machine engineered to break, exactly where it needed to, exactly when it needed to, so it wouldn't break where it would have been fatal. Forget the polished legend of the perfect engineering triumph. That technician with the flashlight, standing over a puddle of kerosene in the middle of the night, he saw the truth before any of us. He just didn't know he was looking at it. The breathing metal protocol begins now. First phase, the cold seam. And it begins somewhere few would expect to find a story about espionage, at a plant processing a metal that almost no one in America truly knew how to mine in sufficient quantity. A warehouse in an industrial zone of West Berlin looks utterly unremarkable. No sign, no guards, nothing to suggest what's happening inside. A truck pulls up to the gate late in the evening, once the streets have already emptied. The driver's paperwork is in order. The bill of lading lists a shipment of industrial raw material bound for a Swedish metallurgical company, a name that means nothing to a casual observer and isn't meant to. The cargo is transferred, papers are processed, stamps are applied. Weeks later, that same metal, having passed through 2 or 3 more transfers like this one, will arrive at a plant in the United States, where it will begin to be machined into parts for an aircraft almost no one knows exists. Almost none of the people in this chain fully understand what they're moving or why. Each link sees only its own small piece of the picture: the cargo, the paperwork, the next destination. This is classic cover architecture. The more layers, the smaller the chance that anyone can assemble the full mosaic. And it's all the more striking once you know what actually lies behind the facade of that Swedish company, that Finnish export office, that empty Panamanian shell. Behind all of it stands the Central Intelligence Agency of the United States, and the metal being moved across 3 borders under false names was mined in the Soviet Union. To understand why this whole multi-stage operation was necessary, we need to step back a few paces, to the point where the engineers designing a next-generation aircraft first run into a problem that seemed to have no solution. The program is born out of humiliation. A reconnaissance aircraft shot down over Soviet territory, a captured pilot, an international scandal, all of it creates a vacuum that needs to be filled as fast as possible. The new aircraft has to fly higher, faster, and stealthier than anything that came before. The calculations quickly lead the designers to an inescapable conclusion. At the speeds the mission demands, an ordinary aluminum airframe simply won't hold up. Friction against the air at 3 times the speed of sound heats the skin to hundreds of degrees. Aluminum loses its strength at that temperature, as if melting from the inside. A different metal is needed, one that stays rigid where everything else warps and sags. The only realistic candidate is titanium. Titanium isn't just a strong metal, it's a metal with an almost mockingly difficult temperament. It's as light as aluminum, but nearly as strong as steel. It holds its shape at temperatures where other materials fail. But it's also monstrously finicky to work with. It reacts with oxygen at high temperature, becomes brittle from the slightest impurity, and demands an alloy purity and a manufacturing culture that, in the late 1950s, exists almost nowhere in the world. And here, the designers hit a wall. In those years, the United States has no domestic reserves of titanium ore of the necessary quality and volume. Existing deposits are either too poor or require a degree of refinement that makes production unprofitable and agonizingly slow for a program measured in months, not years. America is technologically ready to build an aircraft out of titanium. But America doesn't have the titanium itself, or rather, not in enough quantity and purity to supply production of dozens of airframes without delay. The Soviet Union has it. By a cruel twist of fate, the Soviet Union in those years holds some of the richest titanium ore deposits in the world and has already built up experience refining this temperamental metal for its own military and industrial needs. Soviet metallurgy, developed for domestic purposes, turns out to be exactly the source of raw material American engineers need to build a machine designed to fly over the territory of that very same Soviet Union. Realizing this doesn't produce confusion in the offices of the intelligence agency, it produces cold, professional excitement. The analysts face a task that at first glance seems almost absurd: find a way to buy from the enemy the raw material for a weapon aimed at that enemy in such a way that the enemy never learns who the final buyer is or what the cargo is really for. The solution springs from a principle familiar to anyone who has ever dealt in smuggling or money laundering. The longer and more tangled the chain of intermediaries, the harder it is to trace the cargo back to its true recipient. The intelligence agency builds a multi-tiered procurement system through third countries, where Soviet titanium, formerly sold on the open market to unsuspecting trading organizations, begins its long journey through a network of shell companies. The mechanics of this scheme work roughly like this. Soviet foreign trade organizations, eager for hard currency revenue, sell titanium ore and industrial semi-finished products to buyers who look entirely legitimate at first glance, buyers based in neutral or Western-friendly countries. The buyers are companies registered specifically for operations like this: shell firms with minimal staff, no real production base, existing solely to move the cargo through one stage of the chain and hand it off to the next link. The metal changes hands, changes paperwork, changes country of transit several times before it finally reaches an American metallurgical plant working under contract to the defense industry. At every stage of this chain, everything looks clean on paper. Every individual transaction is legal. Every invoice is in order. Every company is properly registered. The Soviet sellers see an ordinary commercial deal with a foreign partner and receive perfectly real currency for a perfectly real product. They have no reason to suspect anything is wrong. Industrial-scale metal is sold all over the world, and it would be strange to expect an ore seller to track the full downstream fate of its product after the sale. It's precisely this ordinariness, this routine nature of international trade, that becomes the perfect cover for an operation whose ultimate goal is to build a spy plane. The intelligence agency operates through a network of intermediary companies in several countries at once, breaking the purchases into batches small enough that neither their volume nor their price draws attention on its own. Part of the metal moves through European trading houses, part through Asian channels, part sits in intermediate warehouses before moving on. This fragmentation isn't accidental. It reduces the risk that anyone, including America's own oversight bodies, let alone Soviet intelligence, could piece together the full picture and grasp the true scale and purpose of the purchases. And here lies the central paradox of this whole story, the paradox worth telling again and again. The Soviet Union, selling titanium through dozens of anonymous intermediaries, is supplying with its own hands the raw material for a machine that will, for years to come, cross its airspace at an altitude beyond the reach of interception, photographing military installations, tracking troop movements, gathering intelligence of the highest strategic value. Every ton of metal mined from Soviet quarries and sold for hard currency literally becomes the skin of an aircraft that will spend years flying unpunished over the territory of its own seller. This isn't just a lucky coincidence. It's an illustration of just how much the intelligence war of the Cold War was fought not only through espionage in the conventional sense, recruiting agents, passing secret documents, but through economics, logistics, and the global trade in raw materials. This particular round was won not by cracking a code or turning an informant, but by a flawlessly built chain of intermediary companies, each one looking, on its own, completely innocent. Soviet analysts, of course, eventually begin to suspect something about the nature of these purchases, about unusual export volumes of titanium in certain years through certain channels. But by the time serious suspicions arise, the aircraft is already designed, built, and flying. The metal has already become part of its frame, its skin, its structural members. There's nothing to be done about it after the fact. The deal is done, the material delivered, the aircraft airborne. The story of the titanium scheme rarely makes it into the popular retellings of this aircraft's legend. It's not as spectacular as tales of record-breaking speed or missile-proof evasion, but it's precisely this story that exposes the true nature of the project from its very beginning. Before becoming a legend of the sky, this machine was the product of a cynical, precisely calculated deception, one in which the adversary itself, with its own hands and its own money, helped build the weapon aimed at it. Every rivet in this fuselage, every panel of its skin carries this irony of the Cold War within it, the enemy's own metal turned into eyes and ears over its own territory. And this is only the first seam in the structure we're about to open up further, because if the beginning of this story is built on deception, its continuation is built on an even stranger paradox, a flaw that turns out, in fact, to be salvation. The smell of kerosene burns itself into memory faster than almost any other scent associated with aviation. Sharp, oily, with a metallic aftertaste, it spreads across the hangar concrete, soaks into the technicians' uniforms, lingers on skin even after several attempts to wash it off. And it was this smell, not the roar of engines or the whistle of air being sliced apart, that greeted anyone approaching this aircraft on the ground. Beneath the fuselage, silence, broken by a single sound. A drop, a pause of several seconds. Another drop. A rhythm, monotonous and almost mocking, echoes through the empty hangar, bouncing off the concrete walls. Fuel trickles down the skin, gathers into thin streams along the panel seams, and falls, landing where a dark, oily stain is already spreading. After an hour on duty, the stain has grown into a full-fledged puddle, reflecting the fluorescent ceiling lights and the vague silhouette of the aircraft itself, looming over the scene like a black deity, bleeding its own blood. Technicians stand nearby in protective boots, instinctively avoiding the wettest patches of concrete, and in their first months of service, almost every one of them feels the same thing, a mix of confusion and near physical discomfort. Before them stands the most expensive, most secret, most advanced flying machine on the planet, a top-tier state secret, a technological miracle for whose sake an entire deception apparatus was built on the other side of the globe, for whose sake titanium was mined and smuggled through dozens of shell companies. And this miracle stands here, in the silence of a nighttime hangar, dripping fuel onto the floor like a rusted faucet long overdue for repair. A young technician, standing his first shift beside this machine, usually reacts the same way. The first thought is panic, a leak, a malfunction. Something has gone wrong. A line is damaged somewhere. He needs to report up the chain immediately, halt any work immediately, find the fault immediately. He crouches down, peers at the dark streak beneath the fuselage, tries to trace the source of the drops by feel, runs a finger along the skin, and finds a gap. A real, physically tangible gap between adjacent titanium skin panels, wide enough for a thin metal probe to slide through freely. And this is where the senior technician steps in, the one who went through this exact same moment of confusion himself, years ago. He doesn't rush to fix the leak. He doesn't reach for the radio. He simply says a phrase that, in the first few seconds, sounds like mockery of every principle of engineering logic. Don't touch it. It's supposed to do that. To understand why an experienced technician reacts this way, we need to drop down to the level of materials physics, to where the real story of this leak begins. The titanium making up this aircraft's skin behaves completely predictably in a laboratory and completely counterintuitively in actual flight. When heated, any metal expands. That's a basic law of physics, familiar since grade school. But how much this titanium expands at the speeds this machine was designed for goes far beyond ordinary engineering experience. At cruising speeds exceeding 3 times the speed of sound, friction against the air heats the aircraft's skin to over 300 degrees Celsius at the most stressed points of the structure. The wing leading edge, the nose cone, certain sections of the fuselage. At that temperature, the metal panels literally elongate, expanding by an amount impossible to ignore in the design process. This isn't a matter of microscopic, invisible changes. This is tens of centimeters of cumulative elongation across the length of the airframe. The engineers face a task that shatters conventional aviation logic. In a typical aircraft, designers strive for maximum rigidity and tightness in the joints. The more snugly the panels fit together, the better the aerodynamics, the less parasitic drag, the cleaner the machine looks. But if you build this aircraft on those same principles, if you fit the titanium panels flush against each other without a single millimeter of gap, the result would be catastrophic. The moment the skin begins heating at supersonic speed and the panels begin expanding, they'll simply have nowhere to go. Rigidly fixed, tightly fitted against each other, they'll start to buckle, deform, generate monstrous internal stresses in the metal. In the worst-case scenario, the skin could begin cracking and failing mid-flight at a speed where any structural damage means instant catastrophe. And that's when a solution is born that looks, on paper, like a surrender to the problem, and turns out, in practice, to be the only way to solve it. The engineers deliberately, intentionally, with meticulous calculation, leave gaps between the skin panels. Not accidental manufacturing flaws, not the result of insufficient time or budget, but precisely engineered gaps, calculated to a fraction of a millimeter for a specific amount of thermal expansion at a specific speed. Every panel is given room to maneuver, freedom to move, expand, elongate, without pressing against neighboring structural elements, without generating critical stresses in the metal. But this solution comes with an unavoidable cost. While the aircraft sits on the ground, while the skin is cold and the panels are at their normal, unexpanded size, those very same gaps remain open. And the fuel tanks of this aircraft aren't separate containers tucked away somewhere in the fuselage, as in most other aircraft. The machine's structural design is such that a significant portion of the airframe's internal volume, including the space between skin layers in certain zones, is used precisely for fuel storage. And when the tank is full and the skin gaps are open, fuel inevitably finds its way out, seeping through these seams under its own weight and dripping onto the tarmac. This is where that image comes from. The one that haunts everyone who sees this machine on the ramp for the first time. Puddles of kerosene beneath the fuselage become an inseparable part of everyday airfield life, so routine that ground personnel stop paying particular attention to it within a few weeks of service. Special metal drip pans exist, wheeled under the aircraft specifically to catch these leaks, because concrete saturated with kerosene begins to deteriorate over time. There's an entire pre-flight and post-flight inspection procedure in which moderate fuel seepage isn't classified as a malfunction, but logged as a completely normal condition of the machine. Picture this scene in the full weight of its visual paradox. A dark hangar. The enormous black silhouette of the aircraft, its sharp, predatory, almost alien fuselage contours, a surface that absorbs light instead of reflecting it. This is a machine designed to fly faster, higher, and more undetected than any other aircraft on the planet. A machine that became a symbol of absolute technological supremacy. And beneath that silhouette, right at the landing gear, stand men in regulation boots, surrounded by puddles of fuel, breathing in the sharp smell of kerosene literally dripping from the belly of the most advanced aircraft in the history of aviation. The contrast is so stark, it's almost impossible to believe both images belong to the same machine. Power and vulnerability, secrecy, and the almost insulting mundanity of the scene converge at a single point, right there on the concrete beneath the fuselage. This contrast is exactly what gave rise to the rumors and jokes among the ground crews at the bases where this machine was stationed. People not privy to the design details sometimes genuinely perceive these leaks as a shameful technical flaw, a symbol that even the most advanced technology has its embarrassing weaknesses. Some technicians, transferred to service this aircraft from other aircraft types, felt genuine irritation at first, considering the leaks a sign of sloppy manufacturing or an unfinished design. It took time and experience to understand that what looks like a shameful defect is, in fact, one of the most elegant engineering solutions in the history of supersonic aviation. The real revelation comes at the moment the aircraft leaves the ground and begins to accelerate. While the machine gains speed at subsonic regimes, the situation changes only marginally. But as the speed indicator approaches Mach 2 and then Mach 3, friction against the air begins doing its work. The skin heats up. The titanium panels, cold and static on the ramp just minutes earlier, begin to expand, exactly as the engineers' calculations predicted decades ago. Each panel slowly, visibly to the monitoring instruments, grows in size, filling that very space, that very gap, that ground personnel once saw as a shameful malfunction. And something happens that can only be called a genuine real-time transformation of the structure. The gaps that, just hours earlier, were dripping fuel onto the hangar concrete begin closing on their own, without a single mechanical movement, without a single hydraulic actuator, purely through the thermal expansion of the metal. The skin becomes genuinely airtight at precisely the moment airtightness becomes vital, at maximum speed, at maximum altitude, where any fuel leak under aerodynamic forces and extreme pressure differential could turn into catastrophe. Precisely where reliability would be least expected from a machine that very morning, was literally weeping fuel, the structure demonstrates absolute, precisely calculated tightness. This is the true essence of the engineering philosophy behind this machine. A flaw isn't a deviation from the ideal. A flaw is part of the ideal, engineered so finely that, at different stages of its existence, the same structural element performs directly opposite functions. On the ground, an open system, allowing the metal to remain at rest without internal stresses. In the air, at maximum speed, a closed, airtight, absolutely reliable structure capable of withstanding loads unattainable by any other aircraft of its era. Technicians who serviced this machine for years eventually came to regard the morning kerosene puddles almost with fondness, almost with professional pride, because they understood what remained invisible to the casual observer. Every drop that fell onto the concrete wasn't a sign of weakness. It was proof that engineers once chose to trust the physics of metal more than the familiar aesthetic of perfectly flush panels. Every puddle was the price the structure paid on the ground to remain absolutely impenetrable up there, high above the clouds, at a speed where a miscalculation would mean the death of the crew. And this is, perhaps, the central lesson of this chapter of our investigation. What looks like weakness at rest can turn out to be the source of strength at the moment of maximum stress. The aircraft that wept fuel onto the hangar concrete didn't do so because it was imperfect. It did so because it was engineered with an understanding beyond most engineers of its time. True strength doesn't lie in rigidity, but in the ability to change, to breathe, to adapt to conditions shifting faster than the human eye can follow. The cockpit's temperature climbs slowly but inexorably, as if some unseen hand is steadily turning a valve deep within the structure. The pilot feels it before he sees it on the instruments. Heat begins seeping through his suit gloves, through the soles of his boots, through the thin layer of air between his body and the cockpit skin. Outside, just centimeters from his shoulder, the metal's temperature is approaching the point at which aluminum cookware melts on a kitchen stove. He knows this. He trained with this knowledge for months, and yet every time the skin temperature needle crawls past another 100 degrees, somewhere deep in his mind, an ancient, ineradicable instinct stirs. Run. There's nowhere to run. He is inside a machine that, at this speed, doesn't merely heat up. It lives in a state pushed as close to destruction as engineering allows, and does so deliberately every single second of flight, across thousands upon thousands of kilometers of the route. To understand the logic of this machine, you have to abandon the most natural instinct in engineering, the instinct to avoid extremes. A conventional aircraft is designed to stay well clear of its limits, to keep a margin of safety, to operate within a comfortable, secure envelope of parameters. The SR-71 breaks that logic entirely. Its engineers didn't try to avoid extreme heat. They built that heat into the very heart of the design, made it not a side effect, but a foundational condition around which the entire architecture of the machine was constructed. At cruising speeds exceeding 3 times the speed of sound, the friction of air molecules against the skin converts kinetic energy into pure, merciless heat. The nose cone and the wing's leading edges, the points absorbing the brunt of the airflow, glow at 315 degrees Celsius and higher. This isn't metaphor, isn't exaggeration for dramatic effect. This is the temperature at which ordinary kitchen-grade aluminum begins to melt. This is the temperature at which human skin suffers an instant, severe burn from mere contact. This aircraft's skin operates at temperatures pressed right up against the structural limit of titanium itself, the metal chosen in the first place precisely because it's one of the few capable of retaining structural integrity under conditions like these. But approaching the limit isn't a safety margin in the conventional sense. It's a narrow edge along which the engineers deliberately charted the machine's flight path. The design tolerances are built so that, under normal flight, the skin heats nearly to titanium's maximum tolerable temperature, but doesn't cross it. The gap between normal cruise conditions and catastrophic material failure is measured in a mere few dozen degrees. The slightest deviation from the calculated flight profile, too long an acceleration, too sharp a maneuver at top speed, too much time spent at the upper end of the speed range, and the thermal margin separating a functioning structure from a failing one begins shrinking fast. This is exactly why the pilots of this machine fly, quite literally, along the edge of fire. Every flight at maximum performance is a controlled approach toward the boundary beyond which the very material the aircraft is built from begins to physically fail. Not metaphorically, not hypothetically, genuinely, in a mode where the titanium skin loses strength faster than the monitoring systems can react. The engineers left the pilot no illusion of a comfortable buffer. What they left him was a precise, narrow corridor of parameters within which the machine operates at the absolute edge of what's possible without ever crossing the line. The very fact that a structure like this can fly at all seems to defy common sense. But this paradox resolves itself through a second, equally radical engineering decision. In this machine, fuel serves not merely as an energy source for the engines. It becomes the aircraft's circulatory system, a fluid that draws excess heat away from the structure's most vulnerable points and carries it off before it can destroy critically important components. The fuel specially developed for this machine possesses unique thermal properties that allow it to function not just as a propellant, but as an effective heat transfer medium. Before reaching the engines and being burned, this fuel circulates through a complex network of lines running through the airframe's hottest zones, along the inner surface of the skin, through the avionics bays, around the crew cabin. It literally bathes, from the inside, the very sections of structure that on the outside are heated to temperatures intolerable for most electronic components and for the human body itself. The electronics housed inside this machine simply could not function under the external heat load without a cooling system like this. Semiconductor components, far more sensitive to overheating than metal structures, require constant heat dissipation, and it's precisely the fuel circulating through the airframe before combustion that takes on this role. The result is a design in which a single resource performs two critically important tasks at once. It powers the engines and simultaneously protects the entire electronic payload from destruction, cooling it just enough to keep the instruments running under conditions that, on the outside, resemble the interior of a blast furnace more than the cockpit of an aircraft. The crew cabin receives its own, separately engineered solution to the same problem. The pilot and the reconnaissance systems officer sit inside a sealed volume that must be kept at a temperature compatible with human life and functioning, while literally centimeters away, outside, a superheated airstream at hundreds of degrees rages past. The cabin's environmental control system uses the same heat exchange principle with the fuel, drawing off excess heat before it can penetrate the sealed volume and turn the cockpit into something resembling an oven. The engineers built an extraordinarily fine-tuned thermal balance in which the fuel system simultaneously feeds the engines, protects the electronics, and keeps the cabin at a breathable temperature. All three functions tied to the same resource, circulating through a single network of lines through the machine's white-hot body. But no engineering system, however elegant, removes the psychological burden from the human being sitting inside this structure for hours at a stretch. The crews who flew this machine lived with a constant, never-releasing awareness that every sortie was flown at the edge of physical failure. This knowledge wasn't abstract technical information read out of a manual. It was part of daily experience, part of the body, part of the nervous system of everyone who flew and serviced this machine. Before every flight, the crew went through a lengthy pre-flight procedure that included breathing pure oxygen for an hour to purge nitrogen from the bloodstream, a precaution against emergency decompression at extreme altitude, where ordinary decompression sickness would mean guaranteed death within seconds. The pilots wore pressure suits nearly indistinguishable from astronaut suits, because at the altitude this machine flew, the atmosphere could no longer sustain human life without complete physical isolation from the outside environment. Every detail of this preparation served as a reminder that the flight ahead was not a routine operation in any ordinary sense of the word. In the cockpit, throughout the entire route, the pilot constantly monitored the skin temperature gauges, knowing that exceeding the calculated parameters by even a few dozen degrees could threaten the structural integrity of the aircraft. He felt the airframe vibrate, heard the distinctive sounds of expanding metal, felt how the machine's behavior shifted as it accelerated and the skin heated. This was a continuous, unbroken engagement with the material at the edge of its physical limits, demanding a level of concentration unattainable in ordinary subsonic flight. Ground crew engineers experienced a similar tension, though in a different form. Every post-flight inspection became a kind of forensic examination. Technicians carefully studied the condition of the skin, searched for the faintest signs of fatigue in the metal, assessed just how close the machine had come to its thermal limits during that particular sortie. There was a constant, never-fading awareness that they were servicing a structure that, by definition, operated near the boundary of its physical capabilities, and that the price of the smallest error in calculation, the smallest deviation from the prescribed flight profile, was measured in human lives. It's in this human dimension that the true scope of the engineering philosophy behind this machine reveals itself. The designers didn't just build an aircraft capable of withstanding extreme heat. They built a culture of operation in which every person connected to this machine's flights had to internally accept and absorb the idea that being pressed right up against destruction was this aircraft's normal, everyday condition, not an anomaly, not an emergency state, just another day at work. This demanded a particular kind of psychological resilience from the pilots, the ability to function with total concentration and precision under conditions the human psyche instinctively reads as an immediate threat to survival. The ability to override the ancient alarm signal the body sends at the sight of white-hot metal in close proximity, and instead place trust in the calculations, in the structure, in the engineers who worked out every degree of this thermal balance long before the machine ever first left the ground. The thermal threshold we've discussed in this chapter wasn't just a physical limit around which the aircraft's structure was built. It was a psychological threshold that every pilot and every technician had to cross within themselves in order to work with this machine day after day, flight after flight, knowing that mere centimeters from their bodies, metal sat at the edge of its own melting point, and that this edge, not some comfortable margin of safety, was the normal operating condition of the fastest combat aircraft of its time. The silence in the cockpit shatters with a single sound, short, sharp, unmistakably identifiable as the warning system's alert. It lasts less than a second, but that's enough for the pilot's entire body to react before his mind has time to register what just happened. Somewhere far below, on the ground or aboard a ship, a launch has just occurred. A missile carrying a warhead capable of turning the aircraft and the two men inside it into a cloud of debris has just left its rail and begun its climb upward toward the machine flying 25 kilometers above, the machine it was fired at. The pilot has a few seconds, not minutes, seconds. And in those seconds, it's decided whether this flight becomes another line in his logbook or the last entry of his life. To understand what happens in those seconds, we first need to understand the very architecture of the threat this machine faces on every combat sortie. The aircraft flies over enemy territory, blanketed with a dense network of surface-to-air missile systems specifically engineered to bring down high-altitude, high-speed targets. Every one of these systems includes a radar station continuously scanning the sky, hunting for a reflected signal, hunting for a target. And an aircraft flying at an altitude unreachable by most other aircraft is still, physically, an object that reflects radio waves, an object that can be detected, an object that weapons can be aimed at. Inside the cockpit sits a dedicated electronic system whose job is to listen to the airwaves, recognize the signature signals of enemy radars, and, critically, distinguish ordinary tracking illumination from that particular distinct radar mode that precedes a missile launch. This distinction matters enormously. A radar can simply be watching the aircraft, scanning the airspace, conducting routine tracking, and in that mode there's no direct threat yet. But the moment the fire control system switches into target lock mode and prepares a missile for launch, the character of the emission changes. The pulse frequency, its structure, its behavior, all of it differs from ordinary tracking sharply enough that specially trained equipment can recognize the shift almost instantly. It's precisely this shift that the warning system on board captures, delivering to the pilot that short, sharp alert tone. Not a vague warning that some radar is operating somewhere. A concrete, unambiguous signal. A launch is being prepared against you, or a launch has already occurred. In the first fraction of a second after the alert, the pilot's body reacts before conscious thought catches up. Pulse quickens, attention sharpens, peripheral vision seems to narrow down to a single task. But years of training override the panic almost instantly. The pilot's response to this signal has been drilled to the point of automation, rehearsed countless times in simulators and in real flights, turned into a sequence of movements the body executes faster than the mind can process it. The pilot's hand moves to the throttle. Not jerky, not frantic, a precise, well-practiced movement that pushes the engine levers to maximum thrust, engaging full afterburner on both turbojet engines simultaneously. And in that moment begins a physical process that will become the primary, the only truly reliable means of defense this machine has against nearly every missile ever built to counter high-altitude targets. To understand why acceleration, rather than an evasive maneuver, rather than deploying flares, rather than any other tactic, became this machine's principal means of survival, we need to look at the physics of the standoff between aircraft and missile in its rawest form. Any surface-to-air missile, to hit its target, must not simply reach the point where the target was at the moment of launch. It has to reach the point where the target will be by the time the missile itself completes its flight, accounting for the target's maneuvers, speed, and altitude. For most aircraft flying at subsonic or moderately supersonic speeds, this is a solvable problem. A missile, possessing far greater speed and maneuverability, can catch and intercept nearly any airborne target within seconds. But this machine flies at speeds exceeding 3 times the speed of sound, at an altitude that in itself creates an additional, critically important problem for the missile. At that altitude, the atmosphere is extremely thin, meaning the missile's aerodynamic surfaces, its fins, its control surfaces, everything that provides maneuverability at lower altitudes, lose much of their effectiveness. The missile has to compensate by burning more engine thrust, fighting the thin air, spending its available energy not on closing the gap toward the target, but simply on maintaining its trajectory at extreme altitude. And this is where the decisive factor enters the equation. As the pilot pushes the throttle to full afterburner, the aircraft keeps accelerating, into a regime most missiles of the era simply cannot follow into. The closing speed between missile and target drops sharply as the aircraft builds its own speed further. A missile aimed initially at an intercept point calculated for a slower or lower flying target begins physically falling behind a target that keeps slipping away. Its own energy reserve, limited by a finite amount of engine fuel, depletes faster than it can close the ever-growing distance to an aircraft that's simultaneously gaining both speed and altitude. This isn't a clever maneuver in the conventional sense of aerial combat. There are no sharp turns here, no attempts to fool a guidance system through abrupt changes of direction. There's blunt, brutal, ruthlessly effective physics. Outrun what's chasing you faster than it can catch you, and climb to where its weapon loses the very ability to function in air too thin for its aerodynamic limits. Many of the missiles fired at this machine physically could not complete their intercept simply because their engines burned through their entire fuel supply before the distance to the target closed to within the warhead's kill radius. Others, even after closing to a relatively short range, lost control effectiveness at extreme altitude, where their aerodynamic fins barely gripped the thin air, unable to deliver the final course correction needed for a direct hit. Still others never managed to reach the necessary altitude at all, ending up tens and sometimes many hundreds of meters below the trajectory of an aircraft that kept accelerating and climbing further, leaving the missile to burn out helplessly somewhere far below. The pilot in the cockpit, during these seconds, doesn't see any of this physics laid out in formulas and graphs. He sees the instrument readings, feels the growing vibration of the airframe under full afterburner, hears the distinctive roar of engines pushed to their absolute limit of thrust, feels himself pressed back into his seat by mounting acceleration. He waits. The seconds stretch out in his perception, each one filled with total concentration, a complete absence of extraneous thought, a pure, almost meditative state of absolute focus on a single task. Wring every last bit of performance out of the machine and hold that regime until the threat is physically, unambiguously behind him. And then comes the moment that every pilot who flew this machine experienced in his own way, but that shared one common thread, a wave of relief, almost physically palpable, washing over him when the alarm finally falls silent, when it becomes clear that the missile has either run out of fuel, lost the ability to complete its intercept, or simply fallen too far behind to pose any real threat. Some pilots later recalled a shiver running down their skin in these moments, their hands trembling faintly for a few seconds as the tension released, their breath held, it seemed, throughout the entire maneuver, finally escaping in one long exhale. This scene, this sequence of the alarm tone, the hand moving to the throttle, the rising roar of the engines, and the final relief repeated itself throughout this machine's entire operational career hundreds and thousands of times, over different points on the globe, over the territory of different adversaries, equipped with different generations of surface-to-air systems. And this brings us to a number that, on its own, sounds almost implausible, yet is documented, preserved in archives, checked and rechecked by aviation historians for decades. Over the entire career of this machine, more than 4,000 surface-to-air missiles were fired at it. 4,000 attempts to destroy this target, made by various adversaries equipped with the most advanced air defense systems of the time, including systems specifically upgraded and adapted precisely to counter high-altitude, high-speed targets like this aircraft. And not one of those 4,000 missiles ever reached its target. Not a single hit in the machine's entire operational history, not one instance where the physics of speed, altitude, and afterburner failed the crew at the critical moment. This isn't luck repeating itself thousands of times in a row. This is statistical proof that the engineering decision at the foundation of this machine, a simple, blunt, almost primitive-looking decision to rely on speed and altitude instead of armor, instead of complex electronic countermeasure systems, instead of intricate evasive maneuvers, turned out to be absolutely, unprecedentedly effective. This result remains unmatched to this day. No production combat aircraft built before or after this machine can claim a comparable survival record against a comparable number of combat sorties and intercept attempts. Modern fighters, equipped with the most advanced defensive systems, the most sophisticated jamming suites, the most refined electronics, haven't come close to this figure because the very nature of their combat employment involves an entirely different character of threats, a different adversary tactic, a different geometry of engagement altogether. The secret of this machine wasn't invulnerability in some absolute sense. The secret was that the engineers built a platform physically unreachable by the weapons of its era at the one moment that mattered, the moment of threat. Every missile launch against this aircraft was, in essence, a race between the energy stored in the missile's fuel tanks and the energy stored in the aircraft's engines. And in that race, repeated more than 4,000 times, the aircraft won every single time, without a single exception. A simple tactic, almost childlike in its essence, just hit the gas, turned out to be the most reliable evasion doctrine ever implemented in the history of combat aviation. Not because it was elegant, but because it rested not on cunning, not on deception, not on chance, but on the blunt, merciless, irrefutable physics of speed, altitude, and energy that no missile of that era was capable of overcoming. May Day, early morning. The sky over the Urals is clear, almost cloudless. Perfect weather for a reconnaissance flight, the worst possible weather for someone trying to remain unseen. The pilot flies his aircraft at its absolute ceiling, the very altitude that, until yesterday, seemed an ironclad guarantee of safety, an untouchable boundary no enemy weapon could reach. He believes in that guarantee. He has to believe in it. The entire architecture of his mission rests on the assumption that altitude alone equals invulnerability. Within minutes, that assumption will be shattered by the explosion of a missile that tears the wing off his aircraft at an altitude that, a second earlier, seemed unreachable by any weapon on the planet. The pilot survives. He parachutes down onto the territory of the country he was supposed to photograph from above, leaving no trace of his presence. He's captured almost immediately, and an international scandal begins on a scale that will define, for decades to come, the very logic of how one superpower builds any machine meant to peer over the horizon of another. We opened this film with the image of a technician standing in a puddle of kerosene beneath an aircraft that looked broken but wasn't. Now, at the very end of our investigation, it's time to return to the origin of this story, to the point where not the design itself was born, but the very reason that design ever had to exist at all. The incident involving Gary Powers and his reconnaissance aircraft remains one of the most painful chapters in the history of American intelligence, not because a costly piece of equipment was lost. Hardware can be rebuilt. Aircraft can be replaced. The real wound, the real trauma left behind by this event, lay elsewhere, in a living human being taken prisoner, paraded before cameras, used in a show trial, turned into an instrument of public humiliation for an entire country in front of the whole world. A downed aircraft could be written off as a technical failure. A captured pilot, forced to testify before hostile journalists, became a political catastrophe unfolding over weeks, over months, leaving a mark that couldn't be erased by a simple apology or a replacement of equipment. It's precisely at this moment that a requirement is formulated in the offices shaping the future of American aerial reconnaissance, a requirement that, at first glance, sounds almost absurd in its bluntness. But that would become the foundation for the machine we've been telling you about throughout this entire film. The requirement is roughly this: never again. Never again should an aircraft from this program end up in a situation where it can be shot down and its pilot taken alive. Not reduce the probability of such an outcome. Not improve the statistics. Eliminate the very physical possibility of this scenario repeating. This requirement, simple in its wording, turns out to be monstrously complex to translate into engineering. How do you build a machine that cannot be shot down? Not harder to shoot down, not more difficult to hit. Simply cannot, in the literal, physical sense of that word, given the level of enemy weapons development that existed at the time and for the foreseeable future. And this is where the picture we've assembled piece by piece throughout this entire investigation truly comes together. A picture that can only be fully understood now, seen as a whole, in light of the trauma that gave rise to its very necessity. Recall the titanium scheme we opened this investigation with. Why was this whole elaborate, risky, cynical mechanism of buying metal from the enemy through dozens of shell companies even necessary? Because only titanium can withstand the heating produced at a speed that makes an aircraft physically unreachable by the interception weapons that existed at the time. The ordinary aluminum airframe used in this machine's predecessor simply couldn't withstand the speeds necessary for absolute unreachability. A new generation metal was required, and it had to be obtained by any means necessary, even at the cost of a deal with the adversary itself, because the alternative was another film reel, another pilot in front of the cameras, another international scandal. Recall the leaking fuel tanks, the puddles of kerosene the technicians stood in, staring at a machine that looked broken. Why did the engineers deliberately leave gaps in the skin, going against the very nature of what an aircraft's structural ceiling is supposed to be? Because a rigid, perfectly flush structure would simply have torn itself apart at the speed and temperature required to achieve unreachability. The flaw that provoked confusion, even shame, in an unprepared observer turns out to be a direct, literal answer to the question posed after Powers' capture. How do you make sure an aircraft's speed is never, ever insufficient again? Recall the extreme heating of the skin, the temperature edging toward the melting point of the metal itself, and the fuel turned into a coolant to protect the cabin and the electronics. Why push so close to the boundary of physical structural failure? Because it was exactly there, at the very edge of what was possible, that the speed regime began, where no missile of that era could physically keep pace with the target. The thermal threshold we discussed wasn't a symptom of engineering recklessness. It was the price the structure was willing to pay for absolute protection against a repeat of the events of 1960. And finally, recall the just hit the gas tactic, the 4,000 missile launches that never once found their mark. This isn't just an impressive statistic on its own, it's statistical proof that the requirement formulated after the captivity of a single man was fulfilled literally, with absolute engineering precision. Not one missile ever reached this machine, not once, across its entire operational career. No pilot who flew it ever experienced anything even remotely resembling what Gary Powers experienced over the Urals. Every element of the design we've unpacked throughout this film as a separate engineering puzzle, a separate paradox, a separate detail of brilliant technical problem-solving, turns out, in fact, to be part of one single, unified, complete answer to one single trauma. Not a collection of random engineering successes, not a series of separate inventions that happen to fit together into a coherent design later on. A single, consistent, ruthlessly logical philosophy, grown out of one simple, almost animal imperative. Never again allow the enemy to take prisoner a man who flew over that country's skies on a secret mission. This philosophy is stated with brutal clarity and brutal simplicity. If you can't be shot down, you can't be captured. Not protecting the pilot with armor. Not protecting the aircraft with maneuverability. Protection through the sheer fact of physical unreachability, built with such engineering consistency that, over decades of service, this machine never once confirmed the single scenario most feared by the people who ordered it into existence. This machine was retired from service decades ago. Technology has advanced enormously since its last combat sortie. New generations of missiles have appeared, new radar systems, new principles of air defense architecture, capable of handling targets no one even imagined at the time this aircraft was built. And yet this machine's survival record, an absolute 0 effective hits out of thousands of enemy missile launches, remains unmatched to this day. Why has no aircraft built after it, including machines equipped with technology unimaginable to the engineers of that era, even in their boldest speculation, ever managed to replicate this result? The answer doesn't lie in the realm of technology. It lies in the realm of design philosophy. No subsequent program was ever built around such an absolute, such an uncompromising requirement of physical unreachability. Modern combat aircraft are designed around an entirely different logic: reduced signature, integrated electronic countermeasures, distributed defense systems working in concert with other assets. These are reasonable, effective, contemporary approaches to a fundamentally different character of threat. But none of them sets for itself the same, extremely narrow, extremely radical goal: making the aircraft an object the enemy's weapon is physically incapable of reaching at all. That goal wasn't driven by abstract technical ambition, by a desire to set a record for the sake of a record. It was driven by the living memory of a man sitting in front of hostile cameras, by an international humiliation the country refused at any cost to endure a second time. And that's exactly why the machine born from that memory turned out to be so consistent, so uncompromising in every single one of its engineering decisions, from the metal procurement to the design of the skin, from its thermal philosophy to its evasion tactics. Every element wasn't a random discovery, but a direct, hard-earned answer to one specific human tragedy that happened once in the sky over the Urals. The technician standing in a puddle of kerosene at the very beginning of our investigation didn't know he was looking at a malfunction. He was looking at metal tempered by history, a structure forged not merely by the heat of friction against the air, but by the very fire of a humiliation his country had once endured on a spring morning in 1960. Every drop of fuel, every degree of extreme heat, every missile that never reached its target was part of that same tempering process, a process in which trauma is transformed into invulnerability, and a shameful defeat becomes the foundation of an absolute triumph that, to this day, remains unmatched. We've taken this machine apart down to its last seam, its last drop of kerosene, its last degree of white-hot metal. We showed you the titanium scheme, the paradox of the leaking tanks, the philosophy of controlled failure, the afterburner escape statistics no one has ever managed to match since. 5 phases of one protocol, 5 parts of one tempering, born from a single humiliation over the Urals. But this protocol has a 6th phase, and you're the one writing it now. If today's investigation made you look at perfect technology differently, not as a polished legend, but as living, breathing metal balancing on the edge, hit that like button. For this channel, it's not just a number, it's a signal that the protocol worked. If you want us to keep opening up stories like this, machines, events, legends, where the truth hiding behind the polish is something else entirely, subscribe to the channel. We don't tell fairy tales here. We open archives, and make sure to hit the bell so you don't miss the next investigation. Because behind every perfect story, whether it's an aircraft, a building, an era, or a person, there's always a leak point, and we'll find it again. Until the next autopsy.